Good evening. It's nice to be here to speak to you all this evening. Just a little bit of background about who I am. As the slide says, I'm now an emeritus professor of Cranfield University. I retired from the university at the end of October last year, having worked for Cranfield for 42 years in a whole wide range of different roles and activities, but all associated with water resources, and particularly relating to the natural environment and to food supply. So I worked a lot with irrigated agriculture in the UK and internationally. Also worked a lot and worked very recently on flood risk management, particularly how it relates to agriculture and food production. Essentially, I'm a broad hydrologist with a general interest in water, particularly water quantity, and I'm not a specialist in water quality. And my chemistry teacher from school will be very pleased about that because chemistry is definitely not my strong point. So what I wanted to cover in this presentation was to talk a bit about water resources with a particular focus on the southeast of England and looking to the future. So a little bit about where we are at the moment, but particularly about what the next 10, 20, 30 years is going to bring in terms of our water supply and the demand for water resources, particularly in the southeast of England, but with a story that is generally relatable to the whole of UK. And really pose a question at the end, what kind of things might we be able to do about addressing some of the challenges that we face in the future? So as a hydrologist, I have to start off with a bit of basic hydrology 101 and think about where are our water resources coming from? And in this country, we rely entirely on rainfall, precipitation for our water resources. So the rain that falls on the land, a large proportion of that is consumed by plants. So it's water that infiltrates into the soil, but stays in the upper layer of the soil and gets taken up by plants. And that water is then returned back to the atmosphere through what we call evapotranspiration. What's left and what isn't consumed by plants then goes into our water resources. So it's going into our lakes, our rivers, and our groundwater. And it's this stock of water resources that is available to us to use and is available to support wet and aquatic habitats. Now, on that simple diagram, it just shows those three separate boxes, but of course, all the time, water is moving around from one to the other. Water is flowing from groundwater into the rivers, from rivers into lakes, and so on. So we have a dynamic system of water moving between those three stores. But essentially that amount of water, which on average equates to about 2,000 cubic meters of water per person in the UK, that's the water resource that we have to use. And that water resource is supplying a demand, both in situ demands, so the use of water actually in those water bodies. So the environment is what we'd call an in situ water user. The environment, the aquatic life, relies on water being in rivers, water being in lakes and reservoirs to support that life. But in addition, we can abstract water out of those water resources to supply water to our households, so water that we use for drinking, but for washing, for showering, and also water that's going into industry. Water, particularly a large consumer of water in this country is the power generation industry, uses a lot of water for cooling, and in some parts of the country more than others, agriculture is a big user of water for irrigation of crops. And if all three of those demands can be met by the supply, everything is in balance and everything is fine. But what we find is demand for water for households increases, demand for water for industry increases. So the demand for water that's being abstracted from the water resources goes up. And what gets squeezed then is the water for the environment, the water that is left in those rivers, in those lakes, in those reservoirs that supports the ecology. And that's when we start to get problems. We keep enough water for the environment and we don't have enough water for industry or households, or we supply everything that industry and households needs and we put stress on our environment. And that's the situation where we're at the moment. This map here on the right shows the water companies in England, and coloured in pink are those water companies which are assessed to be in, quote, serious water stress. And what that means is that these are areas where abstraction of water, so taking water out of surface water bodies or taking water out of groundwater bodies, is causing environmental impacts, or there is a need for major water resource development to provide more water for domestic and industrial use. So with the exception of what we might recognize there as being the wetter parts of England, the southwest of England, the northeast, the northwest, the rest of England is water stressed. So that means we are taking more water out of our water resources than is environmentally sustainable. And if we focus in on the southeast of England, that is the most water stressed part of the country. So we have a combination of three factors working together to exacerbate that water stress. The southeast of England is an area of low rainfall. You might not feel that right at the moment, having just been through one of the wettest winters on record, but this map here is showing the long-term average rainfall for the UK. So most of southeast England gets on average around 800 millimeters of rainfall per year. So part of the drier parts of the UK, not the driest, but drier. But it's a very densely populated part of the country. 30% of the UK population lives in the southeast of England. So there is a very high demand for water, for domestic water use in the southeast. Consequently, the resources available is only about 500 cubic meters per capita, which is around only 20% of the national average. So it's an area of low supply and high demand for water, and therefore it faces risks of water stress. And if we look to the future, we know that those boxes in that balance diagram are going to change. On the left-hand side, we can expect changes in the supply of water from changes in the climate. On the right-hand side, we know that population is going to grow, so demand for household water will increase. We know that industry is going to expand, so demand for industrial water is going to increase, and the net effect of that is to put a further squeeze on water for the environment, which is already under stress, particularly here in the southeast of England. So I want to go through and look at those future pressures, both on the supply side and the demand side. Now, starting with the supply, we said that all of our water is coming from rainfall. Any changes in the climate in the future, therefore, are going to change how much water is available in our water resources. Now, climate change science is uncertain. We cannot predict with great accuracy what will happen in the future. So what climate scientists do is run lots of different models with different assumptions, look at the range of possible outcomes from those projections. And the 12 little boxes there on the diagram show a number of different projections for the change in summer rainfall in southeast England for the period between 2040 and 2059 compared to 1981 to 2000 as a baseline. If I just talk through how to interpret what those different boxes mean, then going up and down on the vertical scale there, we have increasing climate change impact. So the bottom row in this diagram assumes the lowest CO2 emissions. So if we do everything to reduce our emissions, to minimize, we reach net zero tomorrow, those are the model outputs for the best situation. If the situation is worst, that's the one shown at the top. That's the worst case emissions scenario. Now, of course, we don't know where we are on that scale, but I would say we are nearer the top of that scale than we are near the bottom of that scale based on what we've been seeing going on. The three columns going from side to side represent the outputs from different models. So based on different modeling, different assumptions, some models show changes in one direction, some show changes in another, some show more extreme changes. The central column is the average of all of the models. The left-hand column is the worst case models, and the right-hand column is the best case. So if we were to consider the best case models and the lowest CO2 emissions, that's showing then a moderate increase in summer rainfall in southeast England. But the average of the models are all showing, irrespective of the CO2 emissions, a decrease in summer rainfall, around about 10%. And the worst case models are showing much more than 10%, going to the very worst case situation, getting up to about minus 50% change in summer rainfall. So the general projections for climate change for Southeast England is that we may expect to get drier summers and wetter winters. And certainly this winter, we've seen a very wet winter. An increased number of summer dry days. So not only less rain in total, but less days with rain. So getting more dry days. And in the winter, getting rain in more big storms, which leads to more rapid runoff and more flooding. Again, we've seen exactly that case this year with flooding over very large areas of the country. So when you put these climate change projections into water resources models, it projects that there'll be decreased summer river flows, so less water in the rivers in the summer for abstraction and to support the ecology. Decreased groundwater recharge, and I put a question mark about that because I'll come back to it in just a moment, but the projections from the climate change risk assessment and the UK climate change programme suggested decreased recharge and therefore lower groundwater levels. So for areas of the country that rely on groundwater for public water supply, this means less water available. Those rivers that rely on groundwater to sustain low flows in the summer, like chalk streams, again, less flow. As a consequence of that, the projections suggest an increased likelihood of summer drought. And to put that into context, 1995 was quite a significant drought in England. Looking at historical data, that has a probability of around 1 in 10 years. So on average, 1 year in 10, we would have expected a dry summer like 1995. Based on the future climate modelling, that comes down to about 1 in 5. So almost a doubling of the frequency of those dry summers and droughts, and an increased chance of what we call unprecedented hot and dry summers. So the real extreme droughts are going to be more likely in the future, and a heightened risk of consecutive dry winters. This is particularly important for water resources because we fill our reservoirs during the winter. We fill our groundwater during the winter. If we have one dry summer, we may be able to cope with that. But when we get 2 dry winters in a row, we don't refill those water resources, and then we have big droughts. And those of you that are old enough like me to remember the drought in 1976, well, no, that was made worse because we'd had a dry 1975 followed by a dry 1976, and we didn't refill the reservoirs at the end of 1975. So the likelihood of those kind of events, the double dry winter, is projected to increase. Now, I mentioned about groundwater recharge. So this is water which then percolates through the soil, goes down into the geology, and contributes to the groundwater reserves, which is critically important for public water supply in many parts of the country, and critically important for sustaining summer flows in rivers, particularly for chalk streams. And some recent modelling carried out by the British Geological Survey suggests that perhaps because of the projected wetter winters, although the period over which recharge is taking place may be shorter, having more rain during that period could lead to increased groundwater recharge. And the kind of thing that we've seen this year, where we've had very wet January, very wet February, would have led to a lot of water going into our groundwater, raising our groundwater levels, which then provides a store of water for the summer, which would be good news for those areas that rely on groundwater if we take out the bad news from having a very wet winter. But one caveat is that this modelling does not take into account changing rainfall intensity. And one of the things that the models of climate change are projecting is that rainfall intensity is going to increase, which means the water doesn't have the chance to percolate into the soil and down into the geology, has a much greater chance of running off, flowing over the surface, causing localized flooding, and not getting down into the water resources where we want it to be. So really the climate change impact on groundwater, particularly in the southeast of England, the jury is still out about whether the climate change may make things better or may make things worse. So overall, in terms of supply of water resources in the southeast of England, we are going to expect lower summer river flows, possibly lower groundwater levels as well. If we look at the other side of the equation about the water demand, well, the first thing is we know that the population is going to increase. Currently, the population of southeast England is about 19.5 million people. There are various projections, depending how things change in the future, how planning goes ahead in the future. The average estimate is about an increase of 3.3 million people by 2050 and an increase of 6.2 million people by 2100. Now, both of those numbers, there are large ranges of uncertainty because obviously it all depends on all sorts of factors. But all the projections suggest that the population of southeast England is going to increase in the future, and it could be by up to about 30% by the end of the century. So more people living in the region means more water for the houses, more water for drinking, for washing, for sanitation. And more or less, for every extra person, we increase the water demand by a fixed amount if nothing else changes. Climate change not only affects the supply of water, but actually also affects the demand for water. If we have hotter, drier summers, we tend to use more water in our homes. So if it's hot, we tend to shower more, we use more water for watering our gardens, we use more water for washing for our cars and so on. So whenever we have a dry summer, if there's no constraints, so if there are no hose pipe bans or anything introduced, we tend to use more water in our homes. So again, climate change, we would expect, if nothing else changes, we would expect demand for domestic water to increase. And also, if drought is likely to become more frequent, then we need to build in more resilience into our system. We need to have more capacity, not to cope with the average year, but to cope with those extreme years. When there is a drought, we still need to make sure we have enough water. So that means we need to build in extra headroom into our water resource storage and water resource distribution system so that we can cope with those extreme events, which are projected to occur more frequently. Putting those together, the estimate from Water Resources Southeast is that the drinking water demand, so that the potable water, the water that's coming through our public water supply system, would need to increase from the current level of about 6 billion litres of water per day for the region, on average, to over 7 billion litres of water per day. So about 1 billion litres of water per day extra to supply the grown population, the extra water demand from a hotter climate, the growth in industry and demand for potable water from industry and businesses as well. And even the most conservative projections for the future suggest that if nothing else changes, there will be very significant water deficits by 2050. So we are going to need a lot more water in the southeast of England in the future. On top of that, we're going to have increased demand from other sectors. Now, power generation sector is not a major user of fresh water in the southeast of England. But in other parts of the country, water from rivers for cooling for power stations is really significant. But it may be that reduces in the future, particularly with more renewables and less thermal power. We may be closing down some of our power stations and therefore actually leave more water in the rivers as a result. Agriculture, on average in the UK, is a small water user. On average, only 2% of our water abstractions from rivers and groundwater in the country go to agriculture, but that conceals a lot of regional variation and also conceals a lot of temporal variation. So in certain parts of the country and at certain times of the year, agriculture can be the biggest user of water. Now, in most cases, agriculture is not using potable water from our public water supply, although some of the high-value horticultural cropping that we find in southeast England does use public water supply. But for most of our irrigated production, for crops like potatoes, for carrots, sugar beet and so on, tends to use water directly from rivers and directly from groundwater. So it's competing for the water resources, but it's not competing in the water infrastructure in the same way with our domestic water supply. But given that agriculture is quite a significant water user in the southeast of England, particularly in certain hotspot areas for horticultural production, with drier, hotter summers, we're likely to be expecting the need for more water from our water resources for agriculture. And then the environmental demand. We know at the moment that a large number of our rivers and our groundwater is over-abstracted. 8% of our rivers have water abstraction at a level which is currently assessed to be unsustainable. That means it's causing significant environmental damage, and 28% of our groundwater resources have unsustainable levels of abstraction. So we are already taking more water out of our water resources than is acceptable for the environment. A further 5% of rivers and 15% of groundwater bodies are at risk of deterioration. So it's projected that if we do nothing else to mitigate this risk, then they will also fall into that level of unsustainable abstraction. So we're not in a good place already. 70% of our chalk streams are not in good ecological status, and in a quarter of those, abstraction of water is cited as being one of the contributory factors to that poor status. So we are already taking out more water from our environment than is sustainable. And so we want to reverse that. We want to be able to leave enough water in our rivers, leave enough water in our groundwater to sustain our wetlands, to leave the environment in a good condition. And that means we need to leave more water in the rivers, leave more water in the groundwater, and take less out. So putting all of those pressures together, this chart shows for the 5 regional water resource groupings in England, where the drivers are for future water demand and how big they are. And perhaps the first thing that we can see there is that the southeast of England is the area with the biggest column. Southeast of England is going to need somewhere around 2,400 million litres of water per day of additional water to meet the demand from climate change, to meet the demand from increased population, to meet the demand from increased business growth, and to restore the environment. So the southeast of England is the most significant in terms of the total volume of additional water resources required. And interestingly, climate change is only actually a small part of that. Only about 10% of that total is to compensate for water that we are likely to lose because of climate change. The biggest factor in there is what we call the environmental destination. That's essentially putting or allowing more water to stay in the environment to support the ecology and therefore take less out for the others. Increasing demand from households is very significant in the southeast of England, as is increasing resilience for future droughts. The demand for non-household water is actually quite a small chunk. See the situation, obviously, much less of a problem in the West Country or in the north of England, where it's wetter. Just in case anybody's questioning, I was looking at this afternoon and thought, well, where's the Midlands gone? And the Midlands is split between the north and the east. So the 5 water resource regions in the UK basically split north and east of England. It goes right straight through the Midlands. Putting all of those together, all of those 5 regions, the total estimated shortfall by 2050 is about 5,000 million litres of water per day. Almost half of that is in the southeast of England. So then just to summarise what that is telling us, we are already in a difficult place. We already are taking more water out of our water resources than is sustainable, and that is having impacts on the ecology. Climate change will most likely reduce the water resources and increase water demand. And population growth and business growth will increase demand as well. There's a need to provide greater resilience to future drought risks, but most significantly in the southeast of England, restoring environmental flows to meet future needs is the greatest water resource requirement. Now, some of the things that we as a society might like to think about the things that we can do. On the demand side, one of those is through reducing leakage. So if we are losing 10% of the water in our distribution system, if we could reduce that, we would get more water to our houses by taking out the same amount of water from the environment, or conversely, get the same amount of water to our houses and take less out of the environment. We could look to try and reduce household use. Domestic per capita water use in this country is around 145 litres per person per day. There are some European countries where less than 100 litres of water is used per person per day. So we might question, why are we using so much water per person in our houses, and how could we perhaps reduce that? And we could think about how we could reduce non-household use. So water use in businesses, water use in industries, water use in agriculture. How could we reduce the demand on those sides? And then on the other side of the equation, we could look at new supplies of water, new reservoirs, obviously being able to store more water, particularly if we are going to have increased winter rainfall, less water in the summer. We need to be able to store the water from the winter and make it available for use in the summer. We could look at using water from other sources. I said all of our water comes from rainfall. Well, that's not quite true, because a very small amount of it comes from desalination, taking the salt out of seawater. Maybe we could increase the amount of water coming from desalination. We could think about water recycling. Our household water, the 145 litres of water per person per day, 95% of that goes back. So we take the water into our house, we use it in our house, we put it then down the drain or down the sewer, and it goes to a water treatment plant. It gets cleaned up and usually discharged back into rivers or discharged to the sea. Could we intercept that cycle and use that water again? So have a circular economy for water, where we treat water to potable standards and put it back into our domestic water supply system. And finally, we could think about transferring water between water companies or between regions. So we could see from the earlier maps that not all of the UK is in the same situation. What are the possibilities for moving water around the country from the wetter places where there's lower demand, move it to the drier places where there's higher demand? So I'll just leave that slide up there as something for you to think about, and I'm happy to take questions.